So this week's lecture is over 3.1 and 3.2. There's really no questions from 3.1. It just gives you kind of an overview of the section or the chapter 3. So we're going to focus on probability. And so 3.1, if you read the section, it's a lot on the history of probability and the motivations of the math behind the probability. And I'm not going to ask you who invented probability or where it came from or anything like that. So I'm going to focus on the questions. This section we're asked to become familiar with dice, cards, and the game of roulette. So the first thing we need to look at is roulette. So problems in 3.1 and 3.2, it's going to give you this picture. And this picture is what you would see if you were to play roulette. And there's this board with numbers 1 through 36 plus 0 and 00. So there's really 38 spaces. Oops. 38 spaces. So when you go to talk about probability, there's 38 possible outcomes because we have 36 numbers and then 2 green numbers. There are 36 over 2, so you can see here, you can use your calculator a lot of the times, or you can just know there's 18 red spaces and 18 black. There are different bets you can make. Red or black is one bet, and the house odds are 1 to 1. That means it pays evenly. So if you bet $50 and you win $50. 2 to 1, 12 numbers, columns or sections. So this is a section. If you bet on one of these sections, then say you bet $50, it's gonna, if you win, you're gonna get $100 because it pays 2 to 1. 6 number line, you can bet on any 6 numbers like 1 through 6 or 7 through 12, etc. That pays 5 to 1. So if you want to bet on the 6 number line, that pays 5 to 1. So it'll pay 5 times as much as you vote. The 5 number line pays 6 to 1. The 4 number line, which is a square, pays 8 to 1. The 3 number, it's called a street, it pays 11 to 1. And 2 numbers, a split, pays 17 to 1. Single number pays 35 to 1. So the house odds are 35 to 1, which is different than the probability. The probability you land on a single number is 1 in 38, since there's 38 spots. So here's where you kind of put your money down. If you were betting on red numbers, you put your money here. If you put on black numbers here. If you're betting on the first 12 here, the second 12 here, the third 12 here, odd here, even here, the first 18 or the last 18. And then you can also vote on odd or even. However, 0 and 00 are neither even or odd. And you can't vote on 0 or 00. 0 or 00 automatically means the house wins. So you might have to refer back to this on some of the problems, but it will be given in the problem. Cards, we've seen examples of cards before. There's 52 cards in a deck. There's 13 suits. There's 13 of each suit, right? There's hearts, diamonds, clubs, and spades. The hearts and diamonds are red, and the clubs and spades are black. Each suit contains a card labeled 2 through 10, followed by Jack, Queen, King, and Ace. The face cards are the Jack, Queen, and King, and the picture cards are the Jack, Queen, King, and Ace. So again, if you need to refer back to this or write this down, we'll talk about, what percentage of the deck are picture cards, or what percentage of the deck are hearts and stuff like that. So that's pretty much 3.1. If you read in the first objective, understanding the types of problems that motivated by the invention of probability, if you spend some time on the PowerPoint, it goes a lot on the history of who invented this and 1700s, 1800s, and a little bit about that. So I'm not going to test you on that, so if you don't waste your time doing that, that's fine. So really the questions in this sections are going to come from 3.2. In 3.2, we're going to talk about the basic terms of probability. We're going to learn some terminology. We're going to be able to calculate some simple probabilities, and then how probabilities are used in genetics. And this is kind of a fun section. Though it takes a little bit of knowledge, like we'll talk about various diseases, and to know the disease is recessive or the disease is dominant is important to know. So basic probability terms. An experiment is the process in which an observation or outcome is obtained. If I roll a dice and I get a 3, that's an experiment. My sample space is the set of all possible outcomes. So if I roll dice, I could get a 1, 2, 3, 4, 5, or 6. And an event is any subspace of the sample space. So we're looking at possible events. So these are all going to be subspaces of the sample space. So it can be the sample space itself. So E1, E2, and E3. Here I just rolled a 3. Here I rolled a 2, a 4, or a 6. That would be the event happening if I rolled a 2 or 4 or 6, meaning an even number comes up. And then also E3, a number between 1 and 6 inclusive comes up. So this would be E3 happening. There's a 100% probability that E3 is going to happen, if this makes sense. So we'll get into more of some calculating this. You know, there's a 1 in 6 chance that E1 is going to happen. There is a 3 in 6 or 1 in half chance that when I roll my dice, I get an even number. So there's a 3 in 6 or 1 in half chance that E2 is going to happen. And then there's a 6 in 6 or 1 chance that E3 is going to happen. And this is called a certain event. So notice rolling an odd number is an event, not an outcome. The outcome would be rolling a 2, which would be an element of this event. Now, this is just getting some of the terminology, and don't get too caught up on it. So, some terms: a certain event is an event that equals to the sample space. So you can see here this E3 is a certain event because it's the exact same size of the sample space. An impossible event is an event that equals to the empty set. So I might say the event of rolling a 17. Well, it's impossible to roll a 17 on a 6-sided dice, so this happens never. So this is the empty set. So you can think of it like that. And that's an impossible event. It's never going to happen. So a certain event has probability 1. The probability is 1, and the probability of the impossible event is 0. So we're going to focus on finding probability and odds. So a lot of times people think they're the same thing. They're not. They can be found from each other and they're linked, but they're not the same thing. So let's look at the two things here. Probability, you're going to think successes over total. So if I talk about rolling an even number, how many potential even numbers do I have over the total number, the total size of the dice? So the probability of it happen, it's always going to be a fraction, and it's always less than 1 or equal to 1. So you could think of the probability of it being odd. Well, there's 3 odd ones, right? 1, 3, and 5 are odd out of 6 total. So the probability that it's odd is a half. And the same thing with the probability of it being even, right? 3 out of 6, which equal 1/2. If I add these up, I get 1, which makes sense because it's either even or odd. So think successes over total. So the odds are always, you want to think successes compared to failures. And you're denoted something with this O in front. So here I say the probability of it being odd. But if I wanted to say the odds of it being odd, the odds of me rolling this dice would be odd, would be 3 to 3, right? There's 3 successes. Here, there's 3 successes. And there's 3 failures. Oops. So I can simplify that to 1 to 1. So the odds are 1 to 1. For every 1 success, there's also 1 failure. There's 3 successes to 3 failures. The same thing with even, the odds of it being even. is 1 to 1 or 3 to 3. So just a note here, probability and odds are linked from each other. So let me show you, if I give you probability, I can find the odds. If I give you odds, I can find the probability. So if you're given probability, let's say the probability of E happening is A over B. Then the odds of E happening is going to be A to B minus A. So does that make sense? So if I say it's going to be 1 to 2, the probability is 1 to 2, the odds is going to be 1 to 2 minus 1, which is exactly what we got, 1 to 1, right? So fixing this would be 1 to 1. So if you're given probability, you can find odds. If you're given odds, you can find probability. So now let's say we're given odds of something happening. I'm going to write that as A to B. Then the probability of E is going to be A over A plus B. So depending on what you're given, you can find the other one. So the example here, if I'm given my odds are 1 to 1, then my probability of E is going to be 1 over 1 plus 1, which is a half, which is exactly what it was in this case, right? These are the same case. I'm looking at the odds and probability. And so if I give you one, you can find the other one. And I will do some more examples of this. And it's important to note that if I have A over B, the odds are going to be A. It's always the top number, and then colon, the bottom number minus the top number. And if I give you the odds as A colon B, then the probabilities is A over A plus B. So hopefully that makes sense. There's something in statistics called the law of large numbers. And what that means is if I do an experiment, I have experimental probability. So if I flip a coin 5 times, I might get heads 4 of those times. But I know the probability of getting heads is 1/2. So if an experiment is repeated a large number of times, the relative frequency of the outcome will tend to be close to the probability of that outcome. So this is an example of the coin toss experiment. And if you see, if I do less than 20 coin toss, my probability is all over the place. You know, here it's 0.4, 0.65, 0.5, 0.7, less than 0.5, more than 0.5, and it's kind of jumping all over the place. So the law of large numbers says if I let the number of tosses get large, then my experimental probability is going to the theoretical probability. So these values are not that close to these values are not necessarily close to the theoretical probability in the beginning, but it's getting there, and that's the law of large numbers. So if you let an experiment run a large amount of times, then the experimental probability is going to reach the theoretical probability. So don't get too caught up these questions on the WebAssign. They're meant to be pretty straightforward. So now we're getting into genetics. And for genetics, we kind of have to do some background work before we start. And this starts with George Mendel. And he did this experiment with peas and plants. And it turns out he had white flowering plants and red flowering plants. So he cross-fertilized these pure reds and these pure whites, and it was interesting because at the time everyone thought, okay, well, they're just going to get pink flowers. And it turns out when he did this, he got white flowers and red flowers. And he explained the result was going to be determined by genes, and that there was a dominant gene and a recessive gene, because he had more red flowers than white flowers. Or red, let me think here. Mendel reason that these offspring had to inherit a red gene from one parent and a white gene from another. These plants had one red flower gene and one white flower gene, but had red flowers. So the red flower was dominant. There was a lot more red flowers than white flower pea pods. So the red flower gene was dominant, and he turned out to apply these statistical ideas, and he could be able to predict how many white flowering plants and how many red flowering plants he would have. So he did a Punnett square for the first generation. So he took a red plant, which was a pure red plant, so it had RR, and a pure white plant, so WW, meaning that they'd only been, the generation of this parents had only come from red flowers, and the generation of the white ones had only come from white flowers. And it turned out you always got a red flower. When you crossed a red flower with a white flower, you always got a red flower, a pure red with a pure white, because red is dominant. So you use this Punnett square, which I don't know if everyone has seen the Punnett square before, but to find this Punnett square, you will, let's go to, let's see, I can't draw on top of that. So you will take the R from the mother and the W from the father, or vice versa. Here, the R is from one parent and the W is from the other parent. So this is the Punnett square for the first generation. So he had all these red flowers that had one parent that came from a white flower. So he knew the gene was RW. So then he crossed the RW plants for the second generation. So the second generation of plants were all red. So these were red, but they were RW red. And it turned out he got 1 out of 4 that was white, because a white plant is going to be WW. This is going to be a red plant, but it's going to carry the potential to have a white flower. This is a red plant, it's going to carry the potential to have a white flower. And this is going to be a red flower, but it's not going to pass on the potential to have white offspring. So this will be white. So the only way to get a white flower is WW. So there's only 4 possible outcomes. WW results in 1 white flowered plant. So the probability that it happens is going to be 25% of the time, or 1/4. And then 75% of the time, the flower is going to be a red flowering plant. So you'll do different problems like this in web design, but really what it gets into is genetics. And genetics is very important when we talk about inheriting disease. There's a huge branch of mathematics called biomath that talks about, you know, the probabilities and the statistics in not only gene therapy or genetics, but also in cancer cells and other types of bacterial diseases that reproduce at a certain rate. But things that you'll need to know: cystic fibrosis is a inherited recessive disease. So it looks like the white flowers. You will only have cystic fibrosis if you have 2 recessive traits, meaning both your parents carry it. So your book uses this NC. So N would be not having the disease, and it's usually capitalized because it's the dominant, and C would be having it. So if you come from your parents of NC, then this means that you do not have the disease, but you're a carrier. So this little C means you're a carrier, but you're not sick. NN would not be sick and not even carry it. So would not have cystic fibrosis and would not be able to pass on the gene because they don't even have the gene. Sickle cell anemia is codominant, meaning a person with 2 sickle cell genes has the disease. So if we look at sickle cell being having the disease would be a carrier. If you have 2 of them, you have sickle cell anemia. So you have the disease. If you're NC, you have sickle cell trait. which is a milder, non-fatal type of the disease. There's two other types of diseases that might come up in WebAssign, and that's Huntington's disease, and it's caused by a dominant gene. So if you're NC, you have it. You have Huntington's disease. Oops. You have Huntington's disease. So that's what it means by a dominant gene. And then this disease here, it's a recessive disease, just like cystic fibrosis. So you can think of it kind of being the same idea here. So let's look at some examples from the homework. So we're back to kind of looking at cards. A modern deck of cards contains 52 cards. How many clubs are in the deck? Well, we know there's 13 clubs, right? What fraction of the deck is clubs? Well, there's 13 out of 52. Or you can also think of 1 out of 4, right? Because there's 4 suits and one of those suits are clubs. So both these answers should give you the correct answer. You don't always have to simplify it unless they tell you. But 13 goes into 52 4 times, so you can simplify it. The next type of problem would be they want to know how much money you would win or lose in any case. So you bet $50 on the black numbers. So if we go back to black numbers, that's going to pay 1 to 1. So if it lands on 17, 17 is black. So that means you won, and you won 1 times 50, right? So you bet $50. So this is what you win. If you land on 36, 36 is red, so you lose, and you only can lose the amount you bet, so you lose $50. Now, these can get a little bit more complicated when you bet 2 different bets. So if you bet $40 on the 112 section and you bet $30 on the number 6, you land on the number 2, you lose this 30, but you win 1 through 12 section, 12 numbers. You win twice as much as you bet. So if you land on 2, you win 2 times 40, but you lose 30. So this would be 80 for a total win of 80 minus $30. If you land on a 6, you win both. So you win 40 times 2 because 6 is in between 1 is in the 112 section. So you win 40 times 2 plus 30 times the single number bet, which is 35. Right? Because a single number will pay 35 times as much as you bet. So 35. And you lose 0 for an overall win of whatever that total is. If you land on 33, you lose both of them. So you win 0 and you lose $70 because that's 40 plus 30 for an overall loss of your total here. So 70. So hopefully seeing some examples on your exam or on your quiz. Your homework, there's Watch It. So if this didn't make sense, you can go to the Watch It and see if you can make sense of that. So one thing we didn't really talk about is house odds or true odds. Pretty much you're going to have house odds on everything unless it's like flipping a coin or drawing cards or rolling a dice. So if you ever talk about like if you go to the racetrack or if you go and look at, betting on games, that's always going to be the house odds. So New York Yankees odds of winning are 9-2, and the New York Mets odds of winning are 14-1. So convert the odds to probabilities. So we're given odds, we want probabilities. So for the probability for the Yankees, That's 9 over 9 plus 2. And the probability of the New York Mets is going to be 14 over 14 plus 1. So hopefully this makes sense from what we talked about before, going from odds to probabilities. So look at, if you plug these in your calculator, you're going to find a percentage. Look at which one's higher for the win, because you're looking the odds who would win the World Series, and then you can pick which one that is. And then in the same year, website B gave odds on who would win the World Series, New York Yankees, and the New York Yankees or the New York Mets, and determined which source thought it was more probable for the Yankees to win the World Series. So if we thought the probability for the New York Yankees, I guess I'll just put Y here, would be 3 over 5, and here the probability would be of the New York Mets would be 6 over 7. So compare these two and see which one thought it was more favorable that the Yankees would win. So you only really need to compare these two, right? And which one's larger. 9 over 11. So 9 over 11 or 3 over 5. And remember, your numbers can be different. So if I plug 9 over 11 in a calculator, I get 0.8181. So 0.8181, and if I do 3 over 5, I get 0.6. So website A, in my example, would have a greater probability of winning. So you might want to put it in a calculator and get it in a percentage to compare them, but your WebAssign wants you to enter it as a fraction, so leave it as 9 over 11. And then the last ones we're going to look at are the genetic ones. So here we're looking at cystic fibrosis and the Texas disease. So remember, this one is dominant and this one's recessive. So if we go back up, we know that, oh sorry, this is both recessive. So they're going to work out to be very similar. So here you have to be able to read what the parent is. So one parent is a cystic fibrosis carrier. So this would be NC. And the other has no cystic fibrosis gene. So this is NN. So if I have a parent that's NN and I cross it with a parent that's NC, and I put it in my Punnett square here, then I have NN, because one comes from this parent and one comes from here. This would be NN, this would be NC, and this would be NC. So the child would have cystic fibrosis, meaning the child would have to be CC. So the probability of that happening is 0%, because if I cross these, then there's no CCs in here. Would be a carrier. Well, there's 2 carriers out of 4, so the probability my kid would be a carrier is 1/2. The child would not have cystic fibrosis and not be a carrier. Well, there's 2 out of 4. So these 2 kids do not have the disease and they're not a carrier. So that's 1/2. The child would be healthy, symptom-free. That's 100%. My child is not going to have cystic fibrosis because one of the parent doesn't carry it, and the disease itself is recessive. So I have to have 2 C's to have it. So let's look at this one here. Is a recessive disease characterized if carriers detect tests show that both prospective parents are carriers. So they're carriers, so we're thinking I have a carrier and a carrier, and now I do my Punnett square. And I cross it. So this would be NN. So I have a healthy kid without carrying the disease, a healthy kid that carries the disease, another healthy kid that carries the disease, and then I have a kid that potentially has the disease. So that would have the disease would be 1 in 4. The child would be a carrier would be 3 and 4. Because this kid still is a carrier, even though it has the disease, it carries it. And the child would be healthy, symptom-free, would be 3 out of 4. Because these kids are healthy, they don't have any symptoms, right? Let's put it in. These kids are healthy, they don't have any symptoms, but these 2 kids are carriers, or these 3 are carriers, and then this one ends up having the disease. So you have to be able to read for your parents. So both prospective carriers carry the disease. I have NC, NC, so that gives me my probabilities here. So let me know if you have any questions in this section, and you need to know the disease they're talking about if it's dominant or recessive. Because if we look at the Huntington's disease, the Huntington's gene is a dominant gene. So if I have 2 parents, let's say I have parents that carry the disease, both parents would have the disease. So if I do the Punnett square, it turns out these 3 kids have it with the dominant gene. Because it's dominant, if they carry it, if they have one of the genes, then they have the disease. So they're carriers, they have it. They would only have a 1 in 4 chance of having a healthy kid that doesn't have it or carry it. Let me know if you have any questions.